All right, so if you have any questions on the exam, please visit me after class or before class. Well, normally I'm not here after class, but if you want to talk a little bit after class, that's fine. But we're going to move on. We're starting chapter 7. So chapter 7, the title of chapter 7 is Applications of Integration. So now we start to do some things with this technique, these techniques that we've created. So as we move through this material, just keep in mind that all the techniques that we've established up to this point are fair game. All right? However, the difficulty level of most of these problems when it comes to integration is much lower than what you were doing on this test or what you were doing for homework. So it's kind of like, in terms of integration, we're going to go from here down. But now we're going to be doing some applications, which means that we're going to have to think a little bit about what we're doing. All right? All right, so let's start this out with a refresher on something. Recall that if I were to draw you the xy axes and I put a curve in here, let's say this curve does something like this, and I ask you the question, is that a function? What would you tell me? Is this a function? Yes? Why would you say yes? Because it passes the vertical line test? So, and I would say, you know, kind of with an asterisk next to it, yes, I agree. And the reason is that for every x value, or for any x value that we plug in, there is only one output, right? There's only, for each x, there's one output. And so that happens for every x, and that's why we say vertical line test. As long as the vertical line only hits the graph one time, each vertical line one time, then it passes and we say, yes, it is a function. What we need to get clear now, though, is the language of what we just said. We can say that this y here is a function of x. All right? Y is a function of x. The y coordinate on this graph can be determined if you give me x. You give me x, I give you y, right? Give me x, I give you y. Y is a function of x. And we can write in notation this way. Y equals some function of x, right? Now, do you remember in college algebra, after we determine whether or not we have a function, we can also talk about an inverse? How do we determine if a function has an inverse? Horizontal line test, right? That's what we would do. So would this function have an inverse? Well, if I draw a horizontal line, I'm going to hit twice, and that means it doesn't have an inverse, right? Agreed? Okay. All right, now let's compare that to this picture. Same thing here, x, y. Let me draw something over here. Is this a function? No. Kind of no. All right? In terms of me asking you, is y a function of x? Is y a function of x? No, right? It's, if I plug in an x value, right, there's actually, in this case, 1, 2, maybe 3 different y values that come out. Agreed? So y is not a function of x. To be a function, one input to one output. This doesn't work. So we would say here, you know, y is not, right, is not a function of x. So why am I rehashing all this? This is kind of obvious. You know this already, right? Well, because what we can do here is we can ask the question, well, is x a function of y? Not is y a function of x, but is x a function of y? So if I give you a y value, is there exactly one x? So imagine drawing lines here. I'm only going to hit this blue curve one time, right? Each time I pick a y, there's only one. So it's kind of like a horizontal line test, right? But not really. I'm not checking to see if this has an inverse. I'm actually just trying to reorder this language. I'm saying x in terms of y instead of y in terms of x. So is x a function of y here? Yes. Here, x is a function of y. Right? And so I could write, kind of like this notation, I could write x is some function of y. So this is usually kind of new. I mean, you may have touched on it a little bit in college algebra, but we need to be clear that when someone draws a curve for you on the xy plane, says, is that a function? And you say yes or no. Normally we're just talking about it, that, you know, when we say is it a function, we're saying is y a function of x. But now we need to broaden our scope a little bit. And now if someone asks us, is that a function, your response to that would be, what do you mean? Like, is that a function of x or a function of y? Understand? There's like two possibilities here. So how about this one over here? This right here is a function of x, right? Y is a function of x. Is x a function of y on that one? So pick a y value. Does it go to exactly 1x? No, there's 1x, but you keep going, there's another x, right? So this one, x is not, right, a function of y. So those are two scenarios. Can you think of an example, excuse me, of something that would not be a function of x or y? Circle, right? Think about, draw a circle. You're going to have something that's neither a function of x or y. Pick an x, you're going to go to multiple y values, right? Pick an x, you're going to hit multiple times. Pick a y, you're going to hit multiple times. That's neither one, right? Can you think of an example of something that would be both a function of x and a function of y? Straight line? I think you mean kind of like a sloped line, right? Like y equals x, just the diagonal. I'll just do a general one. It doesn't matter where it is. How about that? This, you could look at this curve right here as being y is a function of x, or you could look at this as x being a function of y. It would be your choice. But it's a function both ways. Understand? In fact, any function of x that has an inverse, so if you pass both the vertical and horizontal line test, then you should be able to do this, right? Try and come up with another one. Just show you it doesn't have to be a straight line. That would pass both the vertical and horizontal line test. So if you wanted to, you could look at this as a function of x, but you could also go this way and look at it as a function of y. Got it? Okay. Now let's begin. Our goal now in 7.1 is to address this idea of trying to find not the area underneath the curve, which is what the integral represented to us, right? The definite integral was the area below a curve down to the x-axis, but instead the area between curves. And there are two different approaches. We have the first approach, which is whenever we have an area where we can slice it into vertical rectangles. And this is going to be when we have functions of x, which is what we were just talking about. What's a function of x versus what's a function of y. So here's a picture. There's a lot on this picture, so let's investigate this. Let's say that we have this blue one is a function of x. So we've got this thing looks like a parabola, right? That is a function of x, right? Passes the vertical line test. Then we have this red one, which is also a parabola. That's a function of x also. And we would like to know the area between them, which is this shaded region. So we do what we would normally do. We try and slice up that region into a bunch of rectangles. And I've drawn one of these rectangles right here. And imagine making those rectangles, smaller and smaller, then getting an infinite number of them, right? And when we do that, and you add up an infinite number of rectangles, that's where we brought in the integral symbol, right? The integral symbol represented that infinite sum. So we just need to somehow come up with a formula that represents the area of a single rectangle. So what I've done is I've taken this rectangle that's here, and I've just kind of moved it to the side over here so I can see it, and I've kind of removed all the clutter that's around it. And then I've drawn the x-axis, and I've taken some measurements. The first measurement is what's the distance from here all the way to the top of my rectangle. So what is it? F of x. So imagine this rectangle could be anywhere in this region, right? In fact, I'm going to have an infinite number of them, but no matter where I put the rectangle, do we all agree that the top boundary, the highest point on the rectangle, is dictated by the function f? F is going to control how tall it is, right? So this upper bound is f of x. How about the distance from the x-axis to here? Well, that's controlled by the bottom. And the bottom function is the red one, right? So there's your g. So the distance from here to here should be the difference between f and g. Just simple arithmetic, right? So I know that the height of this rectangle will always be the difference between f and g. F take away g, right? And then how wide is the rectangle? Well, dx, right? That's what we did when we were doing just standard rectangles. The width was always dx. So my width here is dx. So if I ask you, what's the area of that little rectangle, you're just going to do, this times this, or the other way around, this times this, which is this formula right here, right? It's f take away g, that quantity, times dx. That will give you the area of that one little slice. And then we add them up, right? We add them up. And so when we add them up, we get the integral. Now, it's up here. It's a little bit easier to see up at the top there. So we're going to do an integral. This says, hey, I'm going to do an infinite sum of a bunch of things. What are the things I'm adding up? Well, this is how tall my rectangle is, and this is how wide my rectangle is. Do you see that this is very similar to what we did already? In fact, what if g is the zero function? Isn't this the zero function? Just a flat line? So if I do f take away g, isn't that just going to give me the area under f all the way down to the x-axis? That's what we've been doing. But now what we're doing is we're allowing this bottom boundary to move. It can change. Also, the limits of integration go from where to where? A to b. Now, what are a and what are b? Let's look at our picture. It's the x values, right? And it starts at the left endpoint of our region, and we proceed to let x vary all the way from a all the way through to b, and that's wherever they hit each other, right? In this particular case, it's the intersection of those two curves, which means to find a and b, in this particular scenario, we would actually have to figure out where those curves intersect. And how do you figure out where two curves intersect? Set them equal to each other. So we might have to do some algebra in here. This all makes sense? Sure? Can you all visualize these little rectangles moving through? Can you see? Oh, that was terrible. It goes I'm trying to. Small rectangle gets bigger, and then it gets smaller as we move from left to right as we let x vary from a to b. All right. That's our formula. We'll use it in a minute. We're going to do 8 or 9 examples today. But what about if we have things that are not functions of x? Instead, we have things that are functions of y. Well, all we're going to do, and this is kind of like the big change today, is that we want to be able to kind of extend what we know already into a different scenario. If I have two curves that are not functions of x, so these fail the vertical line test, right? The red one does at least. Then how about if we look at that red curve as a function of y instead, then it would pass, wouldn't it? So what we'll do is we'll turn our rectangles over, and instead of letting our x vary back and forth and move our rectangles this way, we're going to start with our rectangles like this, and we're going to move the rectangles up through the region like this. Does that make sense? So this function that's on the right-hand side, right, to the right, is our f function. It's f of y, not f of x. Our blue curve is going to be the one on the left side. That's g of y, not g of x. And then kind of like I did before, I'm going to take this rectangle. I'm just going to move it down here to get it out of all the clutter up there. And then here's my y-axis. And can you all see this little? Can you see how that's just this right here moved down with the little y-axis there? Yeah? So I'm going to try and take some measurements on this. The distance from the y-axis all the way to this edge is f of y. Because as I move this rectangle along, no matter where it is, right, what is the curve that's dictating this top edge? It's the f of y curve, right? So that's why the distance from the y-axis to this edge is f of y. And then I measure the distance from here to here, which is the bottom edge of the rectangle, which will always be that blue curve. That's g of y, right? So the distance from this left side to this right side should be the difference of those two. So you see this is everything we just did, just turned sideways basically. So then we say, all right, well, what's this little height? Well, that's our little infinitesimal change, right? But not change in x. It's not the width of the rectangle anymore. It's not this way, so it's not change in x. It's the width of the rectangle up and down, which is our change in y instead. So we're going to go dy here. This is f of y minus g of y. Multiply the two together. That's the area of one slice. And then integral adds them all up. What about our limits of integration? You said negative 6 to 2. So instead of our limits of integration being x values, left and right, because we're going to be going up and down, they're going to be y values. So it has to be where these two curves intersect, but they're y coordinate instead. And that's because we're integrating with respect to y, right? So y is, in this case, negative 6. You can see it a little bit. That's not important. It's c is here, and then we move up through to d. Why do we go from the bottom up? Because negative, then up through positive, right? So we go left to right because negative to positive. So when we turn, it's positive to negative. Negative to positive that way. Questions?